Okay, good afternoon. Let's get started. So let's see, I think at this point all of the homework 8s and 9s are graded, and all of the midterms are graded, including the undergrads. So we're getting caught up. We still have some more homeworks to grade after this, and I've continue to prod the graders to get those done. Regarding the undergraduate midterm, I guess I would say the distribution of grades was almost exactly the same as the graduate section, which was very good. So happy to say that. There were, more A's than B's, more B's than C's, and so on. So it's not a L-shaped curve centered at C or anything. It's a top-heavy distribution. There were a couple of low scores that made the average a little bit lower than the graduate section, but only a few points. And so I would say the same comments regarding curving apply, that you could actually say, well, don't curve it at all. For both the graduate and the undergraduate, I decided that I curved the graduate and we have the same distribution, so I curved the undergraduate the same way. So there's a formula on the D2L page of what the curve was. The median score for the undergrads was 84%, and the same formula curves that up to 87.2. And so you should be able to go on the website if you're an undergrad now and see your final curve score and all of the comments. Okay, I think basically, as a whole, the class did very well on both undergrad and grad sections on the midterm. Okay, we have any homework questions or any other questions?
Yes, so the first problem asks us to estimate the core loss and then points us to the appendix with some physical parameters to look at the core. And there's KFE and KGFE, and could you discuss the differences between these different physical parameters and possibly an optimal approach to estimating the core loss there?
Okay, so we'll talk about the appendix today, actually. In fact, I can bring it up. So this Appendix D has some tables of standard ferrite core shapes. So we're going to talk about what KG is and KGFE today and in upcoming lectures. They don't really apply to this homework set, but those things are a measure of how magnetically large a core is as far as geometry goes that we will use to design inductors and transformers. KFE is this constant in the core loss equation, and KFE really is not in this appendix. KFE is a function of the core material rather than the core geometry. So what this appendix is doing is listing different ferrite core shapes and how big they are, what all their dimensions are. But you can make the ferrite core shape out of whatever ferrite material you want, and it's the material that has the core loss equation associated with it. So you can get this shape of core in a good high-frequency, low core loss material, or you can get it in a same core shape in a cheaper, lower-frequency, higher loss material. So to get KFE, you actually have to go to the plot of core loss versus flux density. And I think the problem asks you to look at a figure in Chapter 13 that is claimed to be a typical material, but the problem is saying, let's suppose our core is made out of that material.
1320.
13.20? Okay, thank you. So figure 13.20 has a plot of PFE, the core loss, versus delta B for different switching frequencies. In fact, let's So what it actually has is PFE, the core loss, which is the sum of the hysteresis and eddy current loss, and it's per unit volume. So this is divided by ACLM, the core volume. And then on this axis is delta B, and these are log scales. So this is log plot. And it has lines for different switching frequencies. So it might have this one for FS is 100 kilohertz, and another one that's FS is, say, 200 kilohertz, and so on. So what you have to do really is, I guess there's two ways to approach it. One is you can simply calculate your delta B, and if you know the frequency, then just use the plot and read the value off. That's a perfectly good way to do it. Another way is to use the formula, and we had a formula that was PFE was KFE times delta B to this beta exponent times the volume. And so this formula is the equation of one of these lines. And at a given frequency, you can write the equation of the line and figure out what beta and KFE are. So it's a log-log plot, and the exponent is really the slope. And to find KFE, after you've figured out the slope, you can evaluate 1 point. So do this, get 1 point, plug in delta B here, and plug in this value into here and solve for KFE, and you can get the equation in analytical form. Either way amounts to the same thing. Excuse me. Okay, does that answer it?
Yes.
Good, thanks. Any other questions? Okay, well, guess there have been a lot more people in office hours this week, and also more comments on the discussion boards for the graduate section at least, so I'm watching them and answering those questions, and you might look on the discussion board if you have questions. Okay. Okay, so we've spent the last several lectures talking about basic magnetics and in some detail on magnetics loss mechanisms. And today I want to start using this material to talk about how to design magnetics. And I have a couple of really goals. The first one is so that if you take the lab next semester, you can go in the lab and wind your own magnetics and know how to get started, at least. Get going on having an idea of what to do. And the second one is that in a in a job, if you're going to build power converters, at least if they're more than a couple of watts in power, then you're probably involved with custom magnetics or magnetics that you design yourself. You can get off-the-shelf inductors and things for specialized, or for certain applications like cell phones. A cell phone inductor, there's very high volume and it's easy to buy those from a lot of manufacturers. But if you have a converter with a transformer in it, it has very specialized requirements, and it's very rare that you can find some off-the-shelf transformer that has the number of turns you need and the size you need and all of this. So it's custom, and whoever's in charge of the power stage has to know what they're doing. And so we really get involved with designing our own magnetics. And even if your company doesn't want to go there and you want to hire some other company and pay them to design and build your magnetics, you still need to know what you're doing, because if you're the person responsible for the power stage, you won't get the efficiency and the good design that you want until you figure out what's going on and make it work the best you can. Okay, so we're going to talk for several lectures now about design of these things, and we're going to start with the basic issue of designing an inductor. Yeah, that's where we'll start. So say we have a buck converter or a boost converter or something, and it requires say a filter inductor in the output. And how do we design this inductor? And you will go into the lab then, if you take the lab next semester, and you'll have some different size ferrite cores in your kit, and you'll have to decide which core to use, how big a core do you need, and you have to decide things like what size wire, how many turns, how big an air gap to put on it. And so where do you start? And what we're going to do here is I'm going to talk about what are the constraints, and I'm actually going to derive a step-by-step procedure for calculating those things so that you can actually work out the numbers and do it. Now, we debate every year among the faculty of whether to teach a step-by-step procedure or not, because we can't account for everything. Especially we can't account for proximity loss because we haven't even chosen a core. We don't know how many layers there are going to be. We can't calculate proximity loss at the beginning. So we'll leave out certain things like that. And what we're going to start with is just include the DC resistance of the wire in our design process. But the step-by-step procedure then will give us what you could say is a first-pass design. And once you've done that design and figured out what the core is and how many turns there are and so on, then you can go back and analyze it and see how big is the core loss and the proximity loss, and is it going to work well or not. And if you have out-of-control proximity loss, then you can iterate the design again. But at least this will get you started so you know what you're doing and how to start and get you in the ballpark. Okay, so design basically involves, in this case, writing down what all the constraints are and then solving them to in some way optimize the design. And so for the case of the filter inductor, we've been modeling our filter inductors with an inductor and a resistor in series that models the DC resistance of the wire. or maybe the AC resistance or something, but we'll call it the DC resistance for now. And so this goes inside our buck converter. We know what the waveforms are. In fact, presumably we've already designed our buck converter. We know what inductance we want. We know what current waveform we're going to apply to the inductor. And now we want to design the inductor to meet those requirements. So we want to have a certain inductance. It needs to carry a certain peak current. So we can draw our current waveform and find what the worst case maximum current is that our inductor has to carry. And we want it to carry that current without saturating. And then also we're going to specify the resistance of the wire. So we'll say there's some, say, DC resistance of the wire. And we want to design our inductor to have no more than some maximum amount of DC resistance, which really is a specification of how much loss are we going to allow in our inductor. So if you know the RMS current and you know the resistance, you can figure out how much power loss that is. And we may say, okay, this is a 100-watt output converter. Maybe I'll allow 1 watt in my inductor. And so then I can calculate how much resistance that corresponds to and use that in the design. Okay. Here is a slide from the last chapter on the inductor, and we're going to assume that the inductor we design is at least topologically equivalent to this. So it has a winding on a core, there's an air gap, we have this model of the magnetic circuit. We will assume the reluctance of the core is very low compared to the reluctance of the gap, which we've already talked about. So we get this equation to solve the magnetic circuit. And we're going to assume then that this is the basic geometry. Now, when I say topologically equivalent, why am I saying that? And so just for a minute here, here's a ferrite core. It's actually it's an inductor that is wound on a magnetic core that will be in the parts kits next semester. I don't know how well you can see that, but it's got the red here is some copper wire. It's pretty fat wire, like number 15 or 16 gauge wire. It's got the dark gray is the ferrite core. The wire is wound on a plastic bobbin that has pins here that plug into a printed circuit board. And this is what's called a PQ core. It's actually a, what is it, a PQ 2620. So here's what the ferrite core actually looks like. These numbers on the core are generally related to the dimensions in millimeters. This core, this distance here, this is kind of tricky to be coordinated and do, but this distance from here to here, here to here, is 26 millimeters. Okay? And then when you stack the two core halves together to get one complete core, the height is 20 millimeters. Okay? So bigger the number, the bigger the core is for real. So it comes with a plastic bobbin, and you're supposed to wind your wire on this bobbin around like this. And then you put the core over it. Okay. And you clamp it together, and it plugs into your printed circuit board. There we go.
So the pins coming off are just stabilizing? They're just structural?
So that pins on the clip on the outside here are stabilizing, and then these pins on the bobbin are for electrical connections. So when you wind you wind it, you can see it, the wire is soldered to two of the pins, and then those pins plug into the printed circuit board. The PQ cores have a square bottom, so they take up a square piece of real estate on the printed circuit board. And the whole core is shaped around that to try to minimize the amount of printed circuit board area. And the other thing that they have that's a nice thing is that they have a round center post. You can see that. So when you put the wire on the bobbin is round, and the wire goes around this round center post, and so the one turn has the minimum length, which minimizes the resistance of the wire. Some cores have square center posts, which are easier to make in ferrite, but they're harder to wind. So a round center post is nice. Okay, probably more than I needed to talk about so far, but this is the basic problem then. You've got a box with different, maybe a box of PQ cores, but they all have different dimensions. Some are bigger than others, and you have to pick which one to use, and then how many turns, and you have to put an air gap. It's hard to see maybe, but this core actually is gapped. There's a little gap there between the two core halves, and what we do, at least in our prototyping lab, is we have shims that are different thicknesses. We have a whole book of shims, and you can choose the one with the gaps length that you want and cut out a piece to fit in each end of the core and put a air gap in your inductor. Yes?
So the cross sections that we've been working with are purely rectangular, whereas these are flared at the ends.
Yeah, so there's,
You don't have to
let's see, there's the shape. So the round center post has an area that you could say is AC, the area of the core, but it's round instead of square. What happens actually is that of the flux that goes in the center post, as it goes around the magnetic path, half of it goes on one leg and half goes on the other leg. And if they design this right, the areas of the two outer legs should add up to the area of the center post.
So it's a wash.
So then it's constant area going all the way around. It's actually not always true. For example, in this shape of core, they may decide that they need to make the outer legs thicker just for mechanical reasons. And so then the flux density will be different at different points going around the core. On the data sheets, the manufacturers give you a number that they call the effective cross-sectional area. And exactly what that means is hard to say. Maybe it's the smallest, or maybe it's some number that when you plug that in to calculate the core loss, the number comes out right. Probably not, though. So it's but it's, you do what you can, what you have to. So. Okay. Okay, so we've got this, and there is some effective area, AC. There's some effective distance around the core, LG, although it doesn't matter because the reluctance of the core we're going to ignore. And so we can now solve this. In fact, we have solved this in previous lectures for how the inductor works given this. So for design now, we need to write the constraints. And so here's a list of constraints. And the first one is that we want the inductor to operate without saturating. So when we put this maximum current in the inductor, we want the flux density inside the core to run at some controlled value that we'll call B max. And B max is something that we choose to be less than the value that saturates the core. Okay, so we will specify Bmax and we'll give ourselves however much margin or design margin or safety factor we want to make this less than the saturation flux density. And so what we can do is go back to the previous slide here, and we had this equation. And what flux is B times the area. So you can plug in that B is B max, and I here is I max, and we get an equation between I max and B max. Okay? And so that's on the next slide. Here's that equation. And you plug in I max and B max. We can also plug in the equation for the reluctance of the gap, and we get this expression that relates I max to B max. So this is our first constraint. Okay? Now in this constraint, I max is given. We've already analyzed our converter and know what peak current we're going to have. B max is given. We have to decide what B max we want to run at. Mu naught we know, but the number of turns in and the gap length LG are unknowns. So we have one equation here and two unknowns. But it's the first constraint, and we'll keep going and generate some more equations. Okay, second constraint. We want to obtain a certain inductance. Okay, so we previously worked out what the inductance is, and we have a formula for that. So I'm not going to rederive that. But here's the formula. So in this formula, L is given. We've already decided what inductance we want. We know mu naught, but we have three unknowns: the core area, AC, the number of turns, and the gap length. So we've added an equation, but we also have one more unknown. Okay? So we'll keep going. Next constraint is the winding area. So I drew this core that looks like this, and there's a hole in the middle of the core that we call the window of the core. And the core has a certain window area that we're going to call WA. And the constraint here is that the turns of wire we're going to put in the core have to fit inside the window. And okay, this is a simple, dumb thing, but it's very important because you can't put bigger wire than fits. And it's a constraint on how much resistance and how much loss our core will have. Okay, so the window area is really a function of the bobbin. And I had this bobbin that we were winding the wire on, and the bobbin fits inside the core. And so there's a certain area in the bobbin available to put wire in. And on manufacturers' data sheets, you have to look at the data for the bobbin that fits in their core to see how much window area there is. Okay, so we're going to pack wire inside this window. And so you can think about that. Say we have round wire, and you want to pack in turns of round wire in there. So we'll draw all these little circles of wire and pack them nicely. If you do a careful job, maybe you can get your winding to look like this and pack the wire very good. But the bottom line is there's only so much you can fit. And we're going to express the total area of the copper in the window, which is just the area of the wire, not counting the wasted area. We're going to say that total area is the number of turns times the area of the wire. So one turn then has an area we're going to call AW. Okay. This AW is, in fact, often called the bare area of the wire. And so if you look on wire manufacturers' data sheets, they'll talk about the bare area, and what they mean there is that there's some wire and then there's some insulation around the wire. And the bare area is the area of just the copper, not counting the insulation. Okay, so the total area of copper in the window then is the number of turns times the bare area of one turn. And on the other hand, the core window area is WA, and so we need this area of the copper in AW to be less than the window area. And not only that, but we put this fudge factor here, KU. It's called the window utilization factor, and it's some fraction less than 1. And this is because the wire doesn't pack perfectly in the area, in the window area. So we waste space between turns in these little holes here. In fact, there's a big long list of reasons why we can't fill the window with wire, and here's a list of them. So the round wire doesn't pack perfectly, so that reduces the fill factor or utilization factor down to something like 0.7 to 0.55, depending on how you wind it. And those are kind of rule of thumb or typical numbers. Then we have insulation on the wire. If you use what's called magnet wire, the copper magnet wire just has a very thin varnish on the outside, and the insulation is very thin. Magnet wire can take about 60 or 70 volts before the insulation breaks down. It's just a very thin layer of varnish. Oops, what happened? On the other hand, you can, with higher voltage insulation, it's thicker, and then you get KU gets reduced by more, like maybe 0.65 instead of 0.95. Then we have a bobbin that goes in the window area, and the bobbin takes some space and uses up some of the area. And we may have to put tape or more insulation between windings if we have some high voltage breakdown requirement. So there's all this stuff we put in the window that uses up window. So really you have to multiply each of these factors together to see what the total fill factor is going to be. But I'll tell you just some rules of thumb. If you're building a low voltage inductor like a buck converter in the lab that's doing 10 or 20 volts, then you can get a fill factor of around 0.5. If you're building more specialized things like an offline transformer that has insulation or a high voltage transformer that has a lot of insulation, you have a lot lower fill factors. It might go down to 1/4 or even less than 1/10. And on the other hand, sometimes you see people using specialized conductors that aren't round and packed together well. Either a foil winding that's flat foil, or you can actually get almost square wire and pack that together and get fill factors that are more than 1/2. Okay. So our third constraint is this then. Fill factor times the window area has to be greater than the number of turns times the area of the wire in order to get the wire to fit inside the core window. Okay, this is another equation, but it has more unknowns again. We have the area of the wire and the window area are unknowns. Finally, we have one more equation, which is the resistance of the wire. So we want to design to get a certain resistance. And here's the formula we've been using for that. Resistance of the wire is the resistivity rho times the length of the wire divided by the area of the wire. Okay, now how long is the winding? Well, that depends on your bobbin, and we talk about something called the mean length per turn, or MLT here. And if you have a bobbin like this and you're winding turns on it, the turns on the inside of the bobbin have a shorter circumference than the turns on the outside, and so the mean length per turn is is the length of your average turn, maybe in the middle of the winding. And the mean length per turn is something that you can also find on the data sheet for the bobbins. So it's a property of the core geometry. So you multiply the number of turns by the mean length per turn, and you get the length of the winding, and you can plug that in here and get this expression for the resistance. Okay, I'll just point out right now, Appendix D, last appendix in the book, has these tables of all these different core geometries. And let's see, here's the PQ core that I was holding up. And 2620 was the one that I was holding up. Here's its cross-sectional area is 1.19 square centimeters. Here's its window area, 0.333 square centimeters. And here's its mean length per turn. Okay, so there's where you go to get that data for your homework problems. At the end of this appendix, there's also a table of the American wire gauge, which is standard wire sizes that are used in the U.S. The higher the number, the thinner the wire. And this is kind of a logarithmic scale. So if you go up 3 wire sizes, you change the area by a factor of 2. Okay, so the second column here is the bare area in thousandths of a square centimeter. So this is the area of just the copper. The next column is the resistance per unit length. So number 10 gauge wire has 32.9 microohms of resistance for every centimeter of length of the wire. One way to calculate the resistance is to just find the length and plug into this table, or the other is to use this formula. Use the formula right here. Okay, just one last thing about that. Number 10 to 14 gauge wire is fat wire that's like what's used to wire houses. So, you know, here we're talking wires that can handle between 15 and 30 amps of current for that size wire. 20 to 24 gauge is what we often use for hookup wire in the lab. So it's more maybe what you think of as more normal wire. And when you get into the 30s and 40s, we're getting the small wire. Wires in the 40 gauge area are like hairs in thickness. They're very thin. Okay. All right, so we've got 4 equations now. So this one was for no saturating the core. The second one was to get the inductance that we want. The third one says the wire has to fit in the window. And the fourth says we get the desired resistance. Okay, so there's 4 equations. Now, if you go right down all the different variables in these equations, there's 3 kinds of variables. This first list here is the core cross-sectional area, the core window area, and the mean length per turn. These are all functions of the geometry of the core. So if you choose a bigger core, you make those things bigger. The next list are specifications, or things that are known. Okay, so we have to specify maximum current, what flux density we want to run at, and so on. And then the last 3 quantities are just complete unknowns that we have to solve for. How many turns, what gap length, and what wire area. Really, the first list are unknowns also. But we have 4 equations, and what do we do with this? So first of all, with the 4 equations, we want to eliminate these 3 things. Once we eliminate them, we'll have one remaining equation that relates these. Okay? And what we want to do is take everything that depends on the core geometry and put it on one side of the equation, and the givens or known quantities we'll put on the other side of the equation, and we'll choose a core that satisfies that. So here is that. If you do that, you eliminate the three unknowns at the bottom, then you put the first list on the left-hand side here, and you put the knowns on the right-hand side. You get this equation. Okay. So what we have to do is pick a core that satisfies this equation. Okay. So the quantity on the left then is a measure of magnetically how big a core is to do a certain filter inductor job. And what we do is we tabulate the left-hand side for all the cores on our list. And in practice then, you plug into the right-hand side and see how big a core you need, and then you go down the list and find one that satisfies this. So the quantity on the left-hand side is called the core geometrical constant. This was Colonel McLyman at JPL came up with this name and this approach in the 1970s. And so he calls this Kg as the geometrical constant, and so that's what we're doing here is applying that approach. And so if we look at the appendix, so here's our PQ20, or our PQ cores. This second column is a tabulation of the geometrical constant for all of these cores. And so you evaluate the right-hand side of the equation, see how big this K sub G needs to be, go down the list and pick the smallest core that will work. Okay? And once you've done that, then we know what our core is, and we know the values of the area and the window area and the mean length per turn. And so then we can go plug in to find the other three unknowns once we've done that. Okay. Little discussion of this. First of all, this Kg number is, you can think of as a figure of merit that says how effectively large a core is. And there's more than one way to choose a geometry to get a certain K sub G. For example, if we, you could make the core area smaller, AC, make AC smaller, and make the window area bigger. And if you make it big enough, you can get back the same Kg. And what this is saying is that by doing this, we're using less core material, but we're winding more turns and putting more wire in the window area. And so classically, we say that you can trade off iron for copper or vice versa in designing your magnetics and do the same job. So this is another way to say that. Another thing this says is that Kg varies inversely with Bmax squared. If you make Bmax too small, it makes Kg really big. So, it's like, okay, we don't want to saturate our core, and we want to make Bmax less than Bsat, but you don't want to make Bmax any smaller than you have to because the core size goes up really fast. If you make Bmax half as big as it otherwise needs to be, you're making Kg 4 times bigger. And that's making your whole magnetics much larger as well. Kg varies inversely with resistance. If you don't care how big the resistance of the wire is, you can make R big and you can make kg small. And everything else maybe will be the same. So if you don't mind having a mega ohm of winding resistance, you can put 1,000,000 in there and get a teeny kg, smallest core on the list, and get all the inductance and all the current you want, but you just have all kinds of loss in its resistance. So resistance matters. Fill factor also is in the denominator, and that's important. So if you waste window area, you can use a smaller kg if you didn't do that. So we want to pack the wire efficiently into the window to make our inductor smaller as well. So here's the step-by-step procedure that will get you going next semester in the lab. So what you have to do is you have to first figure out all of these things. So these are specifications for our procedure. So wire resistivity, that's probably the resistivity of copper. You have to figure out what is your peak current and how much inductance you want, how much resistance you're going to allow. You have to estimate what the fill factor is going to be, like 1/2, say, and you have to decide on a maximum flux density that you will operate at when the current equals I max. I've also put units here, and units are a continual problem. So these are all MKS units here. Well, not quite. It's ohm centimeters in resistivity. The core dimensions in the equations that follow are going to be in centimeters, not meters. And there will be then factors to convert to meters in the equations. And I do this just because our cores have dimensions that are a couple of centimeters and it's convenient. Okay, so first we evaluate the kg formula that we just talked about. So plug in the values, find a core in the appendix that will work and satisfy this. Once we do that, then we know the values of the dimensions of the core. Okay, next step, we can plug into this formula now to solve for the gap. Basically, the next 3 steps are solving for these, let's see, where are we? For these 3 unknowns. Okay, so we can use the remaining 3 equations to solve for these 3 unknowns. So here we solve for the air gap, and for this equation, AC is in square centimeters. The gap length is in meters, which is strange, but gap lengths aren't centimeters either, so I didn't convert it. You'll have to convert your gap length into convenient units. Our gaps are typically microns or mils. The shims that we will use next semester in the power lab are measured in mils, which are thousandths of an inch. They're not millimeters. So you have to convert to inches. And we get shims that are range typically from 1/2 mil up to several tens of mils. And a long gap is maybe 30 to 50 mils. Okay. Core manufacturers often specify A sub L, which what they do there is they will sell you a core that is already gapped. Comes with an air gap. So you don't shim it. And if you're going into production, you do this. You use these. So A sub L is a measure of how big the gap is. And rather than telling you the gap in actual meters or something, what they do instead is tell you the inductance you get per turn. And so AL is the inductance in nanohenries per turn of wire, or they often also call it millihenries per 1,000 turns. Finally, we can solve for the number of turns in, so you plug into here. In this equation, L, I, and B max are in MKS units. AC is in square centimeters. So there's a 10 to the 4th factor to convert that to square meters, and then we get N. You have to really watch your units. Then we can evaluate the wire size. So this is our formula for how many turns would fit. Basically, you take the available area and divide by the number of turns and use the biggest wire on the table that satisfies this. Finally, I would suggest checking, and one way to check how your design worked is to calculate the winding resistance at the end and see if it meets your requirement. Okay, so that's a good stopping point for today. Basic conductor design, but we'll have some homework on the last homework set to go through a design, and you'll get a chance if you take the lab to do this yourself. Okay, see you Friday.